All right. We shall now abandon the weak field limit. We will abandon our perturbation approach. We will abandon the linearized field equations that we have seen so far. Okay? So this was a chapter. We can put it in our bag of knowledge. Now what we're going to do is something different, as I anticipated before. Namely, we are going to use the Einstein field equations as they are, as they should be, but we are going to consider simple systems, such that the symmetries that are embedded in our system can be exploited to get analytical solutions, can be used to have explicit expressions of the metric, given a certain metal distribution, or in vacuum. Okay? Let's do that. And let's start by considering spherically symmetric systems. So, if we have a spherically symmetric system, which kind of coordinates is nice to use? Cartesian? Better spherical coordinates. And now the coordinates, so our three-dimensional vectors, so this is only the three-dimensional part, are going to be r, the angle theta, and the angle theta, and the angle phi. That's 3D, eh? If we do that, let's start easy by using just a flat geometry, meaning Euclidean. Then the four interval for the space component, again I'm restricting myself to 3D, so the x cubed plus the y cubed plus the z cube is equal to dr squared plus r squared d theta squared plus sinus square of theta d phi squared. Again, the three-dimensional part. In flat geometry, if we want to measure the circumference of a circle, that's going to be 2 pi r. If we want to measure the surface of a sphere, it is going to be 4 pi r squared. Surface, no, not of a circle, of a sphere. And the infinitesimal element of a surface, the S, is going to be r squared sinus of theta d theta d phi. That's flat geometry. If we now go to the curved space-time, let me move this one here. If we now go to curved space-time, curved space, what we have is something a little bit different, namely that if we are measuring the circumference and the surface of a sphere, we are using a radius. If we are looking for the separation between the center and a certain location, we need to use a different radius. Okay? So we have our sphere. The sphere has radius r, but if you measure the separation, if you want to measure the circumference, you use 2 pi r, which is different than 2 pi r. Okay? So these two guys are different. Same goes for the surface on the sphere. And that's because we are living now in a curved space-time, and the geometry behaves differently. Therefore, we can now use the r square plus r square. That's again the three-dimensional part only, the t square plus sine square of theta, and then the phi square. So this is a, I don't know how to call it radius, but let's call it radius for a fixed r. And this is a radius for a fixed theta and phi. And again, the surface of your sphere is going to be 2 pi r, sorry, the circumference, and 4 pi r square for the surface. But now there is this distinction. The Fourier interval, the full Fourier interval now, is going to be the s square equal to what? G mu nu, the x mu and the x nu. Which in general is going to be, you see there is a repeated indices as usual. It implies a symmetry for all the different directions, for the different coordinates. So we have g 0, 0, c square dt square plus g r r d r square plus g theta theta d theta square plus g phi phi d phi squared, which are all diagonal terms for time, radius, the angle, and the other angle. So now you see that like x0 is ct, as before. xr is equal to r, and x theta is equal to theta, and so on. Okay, so that's how you call your coordinate. Well, there is one missing, let's write it. So x phi is equal to phi. Okay, instead of carrying this x, r, blah, 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 I will just write r phi theta, as you can see here. Then, of course, there are not only the diagonal term in general. Therefore, we need to look also for the mixed terms. And we have plus, so we can just continue with our symmetry, 2g r theta, the r the theta, plus 2g r then phi, the r the phi. And then we have plus 2g theta phi, the theta, the phi. And then we have the parts with the time. So you see these are all the three-dimensional components. And then we have the mixture time and space. So we just continue with 2g0 theta, c the t, then the I use theta, so the theta plus 2g0 phi, c the t, the phi. And then we get rid of them, or most of them, because of the symmetries. So what we are going to drop? we are going to drop. So this one remains. Then we are going to drop this one, and this one. I forgot the 1, 2, 3. There should be 4. Not one missing. It's the time. To G R theta. I forgot that one. No? Yes. 0 R, and then C the T, and the R. Okay. Now this should be all. Why we cancel those? We cancel them because we are the coordinates are orthogonal one to each other. So we have G R theta, which is equal to what? The basis identifying the direction R times E theta. But since they are orthogonal, that's equal to 0. And then we have as well the R phi, same business, E theta, that's equal to 0. And the same is for the R theta phi and the theta phi. And G theta phi, which is E theta E phi, that's equal to 0. Because they are orthogonal. Then also these ones are actually equal to 0, given the symmetries that we are employing. Because we can, you see that there are, the C, the T term is common to the two, and we can put them together. See, C the T, C the T. So we can write C the T, and then we just have G0 theta, the theta, plus G0 phi, the phi. But look at this term. You see, I have like it's like a symmetry because I have a repeated index and a repeated index. It means that I can define a vector, so C the T remains there, which I can call VE times the XE, where E now is going to be only theta and phi. You see, I can write it as a symmetry, repeated index, and I can write it in this way. But what's the meaning of that? It means that I have a vector V, which is defined as G0 theta and G0 phi. But a vector is something, is a geometrical object that is pointing somewhere, right? It's giving us a privileged direction. But this breaks the isotropic assumptions that we had at the beginning. This breaks the fact that all directions, because spherical symmetry means that this direction is equivalent to this direction, and so on and so forth. But if we are saying, look, there is a special vector, then we are breaking this assumption. What does it mean? That these two terms must be equal to 0. Because this is a definite no, because of the title, because we are assuming spherically symmetric systems. And things start to getting clear. You see the power of the symmetries that were implemented. They get rid of a lot of terms. And if the metric gets terms, the derivation of the Einstein fields equation will become simpler. We now continue with further approximation. Assumptions. So we are imposing for the metric to be static. Meaning the 0 g mu nu equal to 0. So there is no time dependency for the metric. And 2, we want to have the metric which is invariant under time transformation. What does it mean? That if I do t and minus t, I shouldn't change anything. Okay, if the time is flowing one direction or another, we don't care. And this implies the fact that the component G0R must be equal to 0. See, here is the time, because if this wouldn't be the case, then the 4 interval would change sign. Okay? So we are imposing this, meaning that this cannot happen, and this doesn't happen only if this is the case. We get rid of another term. Doing that, we can find our final, most general metric for a spherical system, which is the S square, which contains all the diagonal terms. So we have J00 C square dt square plus GRR dr square plus the three-dimensional part that is associated to the angles only, which are R square the omega square. Where now the omega, where is it gone? Up there, is referring to this d theta that contains all information about the angles in the metric. Okay? So this is, we can call it the omega square. Which is all of that. And this gives you the coefficients for the g theta theta and g phi phi. Okay? Now, as a convenience for the computation later, you see we are left with only 2 terms that are unknown. And what we wish to do is to perform some computation later when we are going to find out what they are once we plug this metric into the Einstein fields equations. And for convenience, you know that this is in the weak field regime. You know, if you send yourself away from a source, you should get the Minkowski metric back, right? It means that this guy should become a -1. What does it mean? That we could write this G00 term as minus the exponential of some function. Because the exponential is positive. If we put a minus, it's going to be negative. The 2 here is just for convenience. Okay, in the computations, otherwise we should carry the square roots around. It's more convenient to have a 2 here. You can just think that you have this function 2a here. So that's the first part of the metric, so c squared dt squared. Plus, we do the same here. This is going to be at infinite, this is going to be a 1. Because we need to recover the Minkowski metric that we have there at the beginning. And we do the same trick. 2, and then another function b. This is the radial components, and then we have r squared, the omega squared that we are not touching because everything is already defined there. Okay? And in fact, you see that for these are not fixed numbers, but actually these are terms, are functions that in general would depend on time as well. But we are imposing a static metric. And therefore, there cannot be a time evolution for the metric, meaning that R, dependency on R and T, becomes just a dependency on R, on the radius. What is the constraints on this metric, on these functions A and B? They must go to 1, to 0 at infinite. The limit for R that goes to infinite of A of R must be equal to 0, because e to the power of 0 gives you 1. And the same goes for B. Okay, that's why this sort of trick, then you can come out from explicit derivation, you can find out that this is the case, okay? Here I give you the motivation why we can write them this way. And you see that with this trick, A and B incorporates all information regarding the curvature of space-time. Because when we go to infinite, they become automatically 0. They're not there anymore. And that gives you the Minkowski metric back. Nice. Now we have the metric. This is the most general metric that you can use for a spherically symmetric system. What do we do now? We need to understand what are the G0 R and the GRR terms. They are just some function, okay? We don't know how they look like. And how do we find them? Well, we need to associate the space-time to a source. And what do you use? The Einstein fields equations, because that's what they tell you. They associate a metric, so the curvature that is based on a metric, to a source, an energy momentum tensor. Meaning T mu nu. Therefore, we are now targeting G0 R and GRR. Sorry, G00 and GRR. That are the two left ingredients that are left. We are going now to use Einstein fields equations. And what does it mean? That we are going to use G mu nu equal to 8 pi G over C to the power of 4 T mu nu. We need to solve them. What do we need? Well, the Einstein, we needed the Einstein tensor, G mu nu, which is equal to the Ricci tensor, R mu nu, minus 1/2 Ricci scalar, G mu nu. What do we need for that? We need to compute the Christoffel symbol, because with that one we can compute the Ricci scalar, and then we just contract it to get the Ricci tensor. Okay? It's just an exercise. You plug in the metric into here. But you have the metric. It's written up there. So you just have to carry out the computations to find what are your Einstein's field equations. So I will write them for you. So we are going to have G00, 0, which is equal to 1 over R squared, e to the 2a, d over the r, r1 minus e to the minus 2b. Then we have GRR, which are equal to 1 minus R squared, e to b, 1 minus e minus 2b, plus 2 over r, the a over the r. Then we have g theta theta, which is equal to r squared, e to the minus 2b. Then we have phi prime prime. I'm telling you what is prime prime in a moment. Phi prime squared plus phi prime half minus phi prime b minus b over r. And with prime, I mean d over dr is equal to prime. Okay, derivative with respect to r, to the variable r. And then we have g theta theta, which are equal to g phi phi, so that's the same stuff, but it is multiplied by the sinus square of theta, which is an imprint of the definition of the d omega. And you see that in front of the d theta squared there is a sinus squared. So that's an inheritance. That's an heritage of that term. What about all the other terms? All other equations are identically 0. So all other g mu news, blah, 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 they are equal to 0. Why? Because of all the symmetries that we imposed on our metric. You see that from an extremely complex situation, a general situation, through the symmetries, we got something that is relatively simple. And you see that everything depends on these terms, this function, a and b, that fully determines the properties of your space-time. Remember that e to the power of 2a is equal to minus g00. So this gives you this equation constrains the metric. And e to the minus 2b, as it's written there, it's the g rr to the minus 1. Okay, so you see that these equations constrains your oh, this should be, what's that? A, and A. Yes, now it's correct. Okay, good. Now, this is one side of the Einstein field equations, the one associated to geometry. Now we need to work out this object, the energy momentum tensor, and this depends on the source. This depends on the object which is producing the gravitational field, which is producing the distortion of the space-time. And for that, here I'm going to consider only matter. I'm going to consider a fluid. For which I gave you the energy momentum, the equation of the energy momentum tensor, which is T mu nu equal to rho c squared plus the pressure times u mu u nu plus the pressure times the metric g mu nu. P is equal to pressure and rho is equal to density, matter density. If you are considering a stone, then you reduce yourself to, like a planet, you reduce yourself to the case of dust, in which the pressure is equal to 0. If you are considering, I don't know, Jupiter, for example, which is a gaseous object, then there is a pressure content, P. Okay? And then you just specify the scenario that you are considering for the special case. A star is quite similar to that one. It's not complete because stars are producing quite an amount of energy. Okay, so this should be completed. It's not enough what we write there, but you can think of Jupiter as a good representation of this energy momentum tensor. Now, what do we need to compute? These guys, which are the 4 velocities. Remember, 4 velocities intended in this coordinate system. So these are going to be our coordinate r, so a radius, associated to the radius, so r, the time, and the 2 angles. Okay, so one is going to be d theta over d tau squared. Okay, so that's your 4 velocities now. Again, we make our life simple, in which we are asking ourselves for an observer which is at rest with respect to the object and in the center. It means that the object is a kind of, it means that we are asking ourselves for the 4 velocity to be u0, 0, 0, and 0. The time is running, is there, but we are not moving. Okay? So we are at rest with respect to the metric. And just to be clear with respect to what I was saying before, we have that the u0 over the tau, the u0, the x0 square, like that. Then we have u1, which is equal to dr over the tau, and then we have u2, which is equal to d theta over the tau, and the same for the phi. Okay, so that's how you need to understand the 4 velocity for the specific coordinate system that we are considering. What does it mean? That the space components, ue, are equal to 0. It's written here. Then we can also get a value for u0 as associated to the metric. So u0 is equal to e to the minus a. Why is that? Well, because we know that u mu must be equal to minus c squared. So you see, this is constrained. But this is a symmetry, therefore we can explode our symmetry. And what we get is that we have u mu is also equal to what? G0, 0, u 0, u 0, plus g r, u r, u r, plus the other terms. But what are they? They are all equal to 0. Also, when you have the mixed terms, they are all going to be equal to 0. Plus zeros. And this must be equal to that. Must be equal to c squared. This is clearly u0 to the power of 2. So what you do, but there is a minus here. Then what you do, so that's g0, 0, that given what we wrote before is e to the 2a. So we have minus e to the 2a, u0, 0 power of 2, equal to minus c squared. What we do, we just isolate u0, and we get this expression. Okay? So we have this constraint, we just make it explicitly for our case, and we get this expression. Then we have something else. What time is it? Okay, I will conclude here. We have that U0 is equal to minus C e to the power of A. Why is that? Well, for the very same reason. Again, because U mu must be equal to minus C squared. Therefore, when you make this multiplication, which is the only survival term, you want this guy to be equal to minus C squared. Now that we have that, we can compute the energy momentum tensor as it's written up there, because we have the four velocities. All the rest, density and pressure, are a property of our object, of the material composing our object. Just give you briefly the expression. Therefore, we have T00. I write it here again, rho C squared plus the pressure, U0, U0, plus P G00. It looks like this. You see this is 0, 0. Let's be consistent with the indices. This one, we have it. Therefore, we can just plug it here, plug it here. That gives us, in the end, rho C squared plus P e to the 2a, as we have found down there, minus P e to the 2a. These guys are going to cancel out, and what we are left with is rho C squared e to the 2a r. And then we do exactly the same for the other components. So you see it's very simple steps. And with that, you arrive at TRR equal to P e to the 2b of r. T theta theta is equal to P r squared. And T phi phi is equal to P r squared sinus square of theta. And if you wish, is equal to sinus square of theta of T theta theta. That's because this guy is equal to that. All other components are equal to 0. So this guy is diagonal. Now we have everything. Now we have G for the relevant parts of the equations that are non-vanishing. And we can just write explicitly compute our Einstein's field equations. Okay? And this we will do it during the next lecture. So little summary. Little summary. We are now investigating the exact Einstein fields equations, but for a simple object. That's a very different approach with respect to what we have done when computing the linearized version of the Einstein fields equation. This will allow us to find the exact solutions for those equations. Okay, and therefore look at all the aspects that are given by strong regimes in a gravitational for gravitation. So what we did now here was just to give a look at a spherical symmetric object, which is very well represented by spherical coordinates. This is what you get in a flat space. In the curved space-time is the same, except for the fact that the radius of a sphere have to be treated differently with respect to the radius used in computing its surface and its circumference. Having that, we investigated the four interval that in general has all of those terms, diagonal terms, the mixed terms, and so on, many of which disappears because we are considering orthogonal coordinates, And because we want a full isotropic scenario in which no privileged direction can be introduced in our system. Therefore, from these considerations, also the yellow terms here must vanish, must be equal to 0. Then we impose the further assumptions, namely static metric, and we want it to be invariant under time transformations that allowed us to get rid of those terms, write it in this way, and then for convenience, we rewrote the G00 and the GRR term as these two exponentials, just for convenience, for the computations that follows. Then, once we have the metric, we can look at the association of the metric, so how it should become in the end, to the source, to the energy momentum tensor. Therefore, we just had to compute the Einstein tensor explicitly, given that metric, and then assume an energy momentum tensor for the source that we have at hand. In this case, I'm considering a fluid, an ideal fluid, which energy momentum tensor is given by this expression. Then we just put ourselves at rest with respect to our, in the center with respect to our source, and we get these expressions for the energy momentum tensors. Once we have T mu nu and we have G mu nu, we can then proceed and compute and use the Einstein fields equation to find out what are the two coefficients of the metric that are still unknown, and which depend on the source. Okay, different source, different results for those components of the metric. Good. It's too late. You can come down and ask me. I need to conclude here. Thank you very much for your attention, and I'll see you next week.